Hello, students of grade 9. I hope you are all fine. This is a new mathematics session, and in this session, I'm going to revise the lessons included in semester 1 exams in the academic year 2020-2021. The chapters included in this exam are Lecture 4, it was a revision session, in which I revised expanding and factorization. Lecture 9, it is real numbers part 1. Lecture 10, real numbers part 2 of the lesson. Lecture 11, polynomials, part 1 of the polynomials. Lecture 12, polynomials part 2. Lecture 13, I will revise lines and circles. The objectives of this revision are: we will identify kinds of numbers, natural number, integer, decimal number, and the prime number. We will specify real numbers that are rational and irrational. Then we are going to simplify radicals, perform operations with radicals, adding, subtracting, multiplying, and dividing radicals, expand, reduce, and order an algebraic expression, factorize an algebraic expression, calculate the numerical value of an algebraic expression, solve equations of different forms, then define a fractional or rational expression and find its domain of definition. After that, we will simplify a rational algebraic expression. Then we're solving a rational algebraic expression. And then we will identify the relative positions of a line and a circle. Then we will define and draw the tangent to a circle at a given point. Finally, we will apply theorems in math like the midpoint theorem, the median segment theorem, and the Pythagoras theorem. First, I will start with kinds of numbers. A number in mathematics might be, number one, a natural number. When we talk about natural numbers, they are all the positive numbers that do not have a decimal point. Natural numbers example, 0, 1, 2, 3, 4, 5, 6. So all the positive numbers are natural numbers. Number two, integers are all the positive and negative numbers that do not have a decimal point. -4, -3, -2, 0, 1, 2, 3, 4, etc. So they cannot be decimal. Number three, decimal numbers are all the numbers containing a decimal point between their digits. And we know that the point splits a decimal number into two parts, the whole part to the left and the decimal part to the right. As examples, for example, 38.627, 0.09, 1.28, etc. Number four, we have the prime numbers. Prime numbers are all the natural numbers that have only two divisors. These two divisors are 1 and the number itself. All prime numbers are greater than 1. Examples of prime numbers: 2, 3, 5, 7, 11, 13, 17, etc. We know that 0 and 1 are non-prime numbers, and between the prime numbers, 2 is the only even prime number. Now, real numbers in mathematics might be rational numbers. Rational numbers are all the numbers that can be written in the form of a fraction a over b. So any number that can be written as a fraction a over b, we call it a rational number. Examples: 9, we can write it 9 over 1. 0.85 is a decimal number. It can be changed into a decimal fraction, 85 over 100. 0.2, it can be changed into a fraction, 1 over 5. 1.3, it can be changed into a fraction, 13 over 10. Radical 9, it is 3, so it is 3 over 1. negative 11, it is negative 11 over 1. So all of these are called rational numbers. Or they might be irrational numbers. Irrational numbers are all the numbers that can never be written in the form of a fraction. So irrational numbers cannot be written in the form of a fraction. Like the number pi in mathematics. We all know the pi, which is 3.141592. It doesn't end, so it cannot be written as a fraction. For example, radical 7, radical 3, radical 5 over 4, and the last number. These are all called irrational numbers. Some decimal numbers have unlimited and periodic decimal part. What do we mean by periodic? It has repetition in its digits, so they can be written as a fraction. These numbers are rational numbers. For example, 0.2222, it is 0.2 bar. It can be written as a fraction. We will see in the coming slide how can we write it as a fraction. So it is an irrational number. 1.262626 is 1.26 bar. Also, it can be written as a fraction, so it is a rational number. Now let's write rational numbers in fractional form. For example, 0.5, it can be written as 5 over 10. So it is a rational number. 0.48, of course, 5 over 10, we can reduce it into 1 over 2. 0.48, it is a decimal number. It can be changed into a decimal fraction, 48 over 100, and we can reduce it into 12 over 25. 2.4, it can be written as 24 over 10. It can be reduced into 12 over 5. Now 0.6 bar, it is 0.666. So here the periodic is 6. So how can we write it? We write it 6 over 9, and it can be reduced into 2 over 3. So it can be written as a fraction. 0.12 bar, which is 0.121212, it can be written as 12 over 99. We can reduce up and down by 3. 0.312 bar, so the 312 are repeated. So we can write it 312 over 999, and we can reduce by 3. 1.6, and the 6 is bar, so it is 1.6666, so it is 1 plus 6 over 9. So we write 1 over 1, we change them into like fractions, so it is 15 over 9. We can reduce by 3. 3.45 bar, it is 3.4545, so it is 3 plus 45 over 99, and we change them into like fractions, then we get the answer and we can reduce. 1.28686, so the 86 is periodic, so we write 1 plus 2 over 0.2 plus 0.086. So 1 plus 2 over 10 plus 86 over 990. We change them into like fractions and we get the answer. After that, we reduce. This is how we change decimal numbers into, or rational numbers into fractions. Now I will talk about square roots of perfect squares. What do we mean by perfect squares? The radicand can be written as a number square, like radical a squared. The squared cancels the radical and we get a. As examples, we have radical 36. 36 is 6 squared. The squared cancels the radical, so it is 6. Radical 9 is equal to radical 3 squared. The squared cancels the radical, we get 3. So 36 can be written as a perfect squared, it is 6 squared. 9 can be written as a perfect squared, it's a 3 squared. 64 can be written as 8 squared. 100 can be written as 10 squared. And 1 can be written as 1 squared. Now, inside the square root, the radicand might have Number one, a square exponent. So if the exponent inside is already squared, directly we say the square cancels the radical. For example, radical 7 squared is equal to 7. Number two, it might be an even exponent. For example, the exponent inside the radical might be exponent 4, exponent 6, exponent 8. So here we change the exponent into a power of power. The power outside should be square. For example, radical 2 to the power 6. We know that 6 is 3 times 2. So we write it 2 cube, all of it squared. The squared cancels the radical and we get 2 cube. It might be an odd exponent. What do we do here? We change the exponent into an even plus 1. For example, if we have inside the radical a cube exponent or a 5 exponent or a 7 exponent, for example, radical 5 to the power 7. 7 is odd, we change it into the even before it plus 1. So 5 to the power 6 times 5. Here we can split the radical, so 5 to the power 6 times radical 5 is equal to radical 5 to the power 6. We write it 5 cube, all of it squared. The squared cancels the radical, so we get 5 cube times radical 5, which is 125 radical 5. Now we will perform calculations with the square roots. These are important rules here. If we have a number times a radical, for example, a times radical b, it is written a radical b. 3 times radical 7 is written 3 radical 7. 10 times radical 3 is written 10 radical 3. If in the second rule we have radical AB, we can split the big radical into 2, so we can write it radical A times radical B. For example, radical 5 times radical 7, we can write radical, big radical 5 times 7, which is radical 35. We can only add and subtract similar radicands. So if I have 5 radical 2 plus 3 radical 2, since in both the radicand is 2, so we can add the coefficients 5 plus 3, it is 8 radical 2. If I have radical 5 plus radical 3, we cannot add them because the radicand 5 is different than the radicand 3. Now, if we have a big radical and the fraction a over b inside, also in this we can split both. We can write radical a over radical b, and then we can simplify. For example, radical 20 over x to the power 16, we can write it radical 20 over radical x to the power 16, and we can simplify. If the radicand inside is not squared, it is not even, it is not odd, and it is a number. So what should we do here? We should find the prime factors using prime factorization of the radicand, then we simplify. For example, radical 24, it is not squared, it is not, it doesn't have an odd exponent or an even exponent. So we do the prime factorization as I did here for the number 24, and we get the prime factors of 24. Now, instead of 24, we replace it by its prime factors. Then we split the big radical and we get the answer. You have here another example, which is radical 90. Here I have a very important note. If we have a big radical a plus b, it cannot be split into 2 radicands. And if we have radical a minus b, it cannot be split into 2 radicals. We can only split in the case of division of 1 radical and multiplication. Now we will learn how to rationalize the denominator. If we have a fraction and in the denominator we have a radical, how can we rationalize it? Which means I should get rid of the radical in the denominator. For example, if I have radical 3 over radical 2, if I look at the denominator here, I see radical 2. So to rationalize, I multiply radical 3 over radical 2 by a fraction having a numerator and denominator equal to the denominator of the given fraction. So I multiply by radical 2 over radical 2. Now radical 3 times radical 2 is radical 6. Radical 2 times radical 2 is radical 2 squared. Then the squared cancels the radical and I get radical 6 over 2. Now in my answer, as you can see, no more radical in the denominator. In the second form of rationalization, we can see that in the denominator we have a radical, but we also have an operation. Here I have subtraction, so 5 minus radical 3. To get rid of this radical, I multiply by the conjugate fraction. What do we mean by a conjugate fraction? If in the original fraction I have plus, so I multiply both by minus. If I have a minus, I should multiply by the same denominator but with a different sign. Now, after multiplication, I get a fraction without a radical in the denominator. This is how we rationalize the denominator of a fraction, and this is very important. Now, if we have an expression with radicals and we should write it in the form of a radical b, which means one radical only, I look inside each radical at the radicand. If the radicand is prime, as in the case of 3, I leave it. But if we have 27, I make its prime factorization. 12, I make its prime factorization, and 48, I do its prime factorization. Then I replace the 27 and the 12 and 48 by their prime factors. Then we simplify to get an answer in the form of a radical b. Now, we have talked too much about expanding or developing or factorizing an algebraic expression or a polynomial. How can we expand or develop an algebraic expression? Also, how can we reduce it and order it or write it in order? Expand and develop means we should get rid of parentheses by using one of the two rules, either by multiplying or by applying one of the three remarkable identities. What do we mean by reduce? We should reduce the similar monomials, add and subtract them. After that, to order an algebraic expression or a polynomial, we should write the degree or the power or the exponent of the variable in increasing order from the biggest to the smallest. And these are the rules used in expanding an algebraic expression. So either we have the rules of multiplication or the remarkable identities. Please, we should memorize these rules to apply them directly. To factorize an algebraic expression or a polynomial, we should find a common factor between the terms of the polynomial, then divide each term by the common factor. So in rules of factorization, we have these two rules, the rule of common factor or using the one of the rules of the remarkable identities. Now, if you are given a polynomial and you are asked to calculate its numerical value, to calculate the numerical value of a polynomial, we replace the given value of the variable, then we calculate. For example, if we are given this polynomial and we should find a of -1. So each x in the polynomial, we replace it by a -1, then we calculate to get the answer. Please always notice that to calculate the numerical value of a polynomial, this polynomial, the easiest way, it should be written in expanded form to replace. Now, solving equations, if we are given any polynomial in x, to solve it is to find a value for the variable x. Different forms of equation, either we are given a polynomial equal to 0, so here we take the factorized form of p of x, or we are given two polynomials equal to each other, always we take the factorized form of p of x and q of x. If we are given p of x, a polynomial equal to a constant or to a number, here we take the expanded form of the polynomial to be able to solve it correctly. After solving an equation, the solution or the root might be one of these four cases. We might have ax equal b, then the variable x or the root will be x equal b over a. If we have ax equals 0, then here the root x is equal to 0. If we have 0x equal b, this equation has no solution. If we have 0x is equal to 0, here x has many roots or many solutions. Now, how can we solve an equation of the form of two binomials multiplied together or in the factorized form equal to 0? Here, let's look at this form. So here we have two sides. We have side 1, an equal in between, and we have side 2. Always we should make sure that side 2 should always be in factorized form, which means a monomial multiplied by a binomial or a binomial multiplied by another binomial. Side 2 should always be equal to 0. If side 1 is not written in factorized form, we should factorize it first. If side 2, there is no 0, so what we do here is we take everything on side 2, we take it to side 1, and we write 0 on side 2. For example, x minus 7 into x plus 2 is equal to 0. The first side of the equation is written in factorized form, and we have 0 on the second side. So here we take each binomial is equal to 0. So x minus 7 is equal to 0, then x is equal to 7, or x plus 2 is equal to 0, then x is equal to minus 2. In the second one, the first side is not factorized. Here I have, this is the first factor and this is the second factor. Between the first factor and the second factor, we have x plus 2 is common. So we take x plus 2 and we open a bracket to factorize. Then we get rid of the brackets, we reduce the parentheses, and now we have x plus 2 into 3x minus 3 is equal to 0. Side 1 is written in factorized form and side 2 is equal to 0. So we take x plus 2 is equal to 0, then x is equal to minus 2 is the first solution, or 3x minus 3 is equal to 0, then 3x is equal to 3 and x is equal to 1. This is the second root. If we are given x squared is equal to 4, the second side is not 0. So everything on the second side should be taken to side 1. So I will get x squared minus 4 is equal to 0. Now the first side is not factorized. We factorize it using the third remarkable identity. So now it is factorized equal to 0. So we take x minus 2 is equal to 0, then x is equal to 2. Or x plus 2 is equal to 0, then x is equal to minus 2. Now, I will talk about rational or fractional algebraic expression. When I talk about a rational or fractional algebraic expression, I'm talking about an algebraic expression written in the form of a fraction, where the numerator is an algebraic expression and the denominator is another algebraic expression. Here we should always be sure that the denominator of the algebraic expression or the fractional algebraic expression should be written in factorized form. The first thing we start with a rational algebraic expression is writing the domain of definition. What is the domain of definition? A fractional algebraic expression exists or is defined if its denominator is different from 0. So if we have two algebraic expressions, p of x and q of x, a of x is equal to p of x over q of x. So here we replace p of x by its factorized form and q of x by its factorized form. Here I look at the denominator of a of x, I find it factorized. So now I can write something called the domain of definition, which is A of x exists or is defined if whatever we have in the denominator, x plus 4 into x minus 3, should be different from 0. So now we solve. So x should not be equal to minus 4. It should be different from minus 4, and x should be different from 3. Now, after writing the domain of definition, we can simplify or reduce a fractional expression. To simplify a fractional expression, we should find a common factor between both the numerator and denominator. So if we look at this fractional expression, we can see that in the denominator and numerator, we have a common factor, binomial x plus 4. So the binomial x plus 4 cancels the binomial x plus 4, and I get the simplified form of a of x, which is 2x minus 5 over x minus 3. How can we solve a rational expression? To solve it, first we should write the domain of definition. We wrote it before. We should reduce the expression, so we should reduce it to get the reduced form or the simplified form. Then we solve. So if I asked you, solve a of x equal 4, I take the simplified form of a of x equal to 4. Here directly I write 4 over 1, and I do something called, please pay attention to the cross multiplication. I multiply all the numerator by the second denominator and the second denominator by the first numerator, and I write an equal in between. Here I solve an equation as I solved before. So please pay attention to the step of cross multiplication. Now, talking about the circle, what are the relative positions of a line and a circle? If I have a circle and a line, they might be in 3 positions. Position number 1, the line is outside or exterior to the circle if the distance from the center to the straight line is greater than the radius. A straight line in the second position is tangent to the circle at a point, meeting at a point, if the distance from the center to the line is equal to the radius. In the third position, the straight line might be secant to the circle, cutting the circle in 2 points if the distance from the center to the line is less than the radius. Now I will talk about a very important line which is in the circle called the tangent. What is the definition of the tangent? The tangent is a straight line touching the circle from outside at one point, which is here A. Because A is where the tangent touches the circle, then this point is called the point of tangency. If I draw a radius from the center to the point of tangent, it is perpendicular to the tangent, then the radius and the tangent will be perpendicular at A. Two tangents, if they are drawn to the same circle from the same point outside the circle, I will get MA is equal to MB. So if I draw MA tangent to the circle and MB is tangent to the same circle at 2 different points A and B, then the rule here says it is a property. Any 2 tangents drawn to the same circle from a point outside the circle, they will be equal. Then MA will be equal to MB. Now, I will talk about the 3 important theorems that we use in mathematics. The midpoint theorem is applied in all kinds of triangles. If I have any triangle ABC, if I take the midpoint of side AB and N is the midpoint of side AC, the line joining MN, which are the 2 midpoints, will be parallel to the third side BC, and MN will be equal to BC over 2. Now, the converse of the midpoint theorem. If I have a triangle and I draw the midpoint of the first side, if I say I draw MN a line parallel to the third side, then N will be the midpoint of side AC. the median segment theorem in a right triangle. So this is only applied in a right triangle. If I have any right triangle, for example, triangle ACB is right at C. Who's my hypotenuse? Of course, the hypotenuse is AB, which is opposite to the right angle. If we draw the median relative to the hypotenuse, this median will be equal to the length of the hypotenuse over 2. Then CD will be equal to the length of AB over 2. But since D is the midpoint of AB, then CD will be equal to DA will be equal to DB. What's the converse of the median relative to the hypotenuse? If I gave you, for example, any triangle, you don't know that this triangle is right. I should prove that this triangle is right. For example, if I gave you a triangle CBA and I told you draw the median from B to AC such that BM is equal to AC over 2, directly you will say that this triangle will be right at B and AC will be the hypotenuse. Finally, we have the Pythagoras theorem, which is only applied in a right triangle. So if I have any right triangle ABC right at A, who's the hypotenuse? It is BC. So this rule says, or this theorem says, the length of BC squared is equal to AB squared plus AC squared. What's the converse of the Pythagoras theorem? If you are given any triangle, I don't know it is right, I want to prove it is right. If I can prove that AB squared plus AC squared is equal to BC squared, then this triangle will be right at A. Please always keep in mind a very important note here. Always the hypotenuse in a right triangle is the longest side, and it is the side opposite to the right angle. So between AB, AC, and BC, who's the hypotenuse? The longest is BC, so BC is the hypotenuse. So my dear students in grade 9, this was semester 1 revision session that we have before the exams of semester 1. Please watch this video well, understand every single point in it, since these lessons are really very important for this year. And if you have at any time any question, please don't wait until we meet on Zoom. Contact me on WhatsApp and I'll be ready to answer all your questions. Thank you, my lovely students. Love you all and take care. Thank you.